Geometry students, this is lesson 8-4, and it begins on page 327 in print and 327 straight up in Braille, a little over halfway down the page. It has a paragraph of information to discuss what we've learned in previous lessons. So on page 327 and 327 in print, it says, in previous lessons, you studied the properties of quadrilaterals and parallelograms. Now you will learn the properties of three other special types of quadrilaterals: rectangles, rhombi, and squares. The following diagram shows how these quadrilaterals are related. So if you turn two Braille pages to your thermofilm page, 327B, and the graphic right in the middle of the print page, this is kind of a layout of the category of quadrilaterals in relationship to each other. So the very first four-sided figure is the quadrilateral. And then there's a little down line going down to a parallelogram showing parallel and congruent sides. They're labeled off to the right. Then from the parallelogram, there's three lines extending from the base going to three different figures. The one to the left is a rectangle. Notice that it has four 90-degree sides. And the one to the right is a rhombus. It has four congruent sides. The angles are not 90. And the one then immediately below, connected to the rectangle and the rhombus and the parallelogram, is the square. So this is detailing that a parallelogram has opposite sides that are parallel and opposite sides that are congruent. And rectangles, rhombuses, rhombi, and squares are also parallelograms because their opposite sides are parallel and their opposite sides are congruent. Then rectangles are in a category of themselves out of parallelograms, but there is also a square. A square is related to a rectangle because it meets the definition. A rectangle is parallelogram with four right angles. A square then is a parallelogram with four right angles, but it also has four congruent sides. And then a rhombus, which is not related to a rectangle because it has four congruent sides. A square is also a rhombus because it has four congruent sides. But a rhombus is just a parallelogram, but it also has four congruent sides. So quadrilaterals, they're all four-sided figures. Parallelogram, more specifically, opposite sides are parallel and congruent. There's three types of parallelograms. Besides just a parallelogram, we have three more specific types: a rectangle, a rhombus, and a square. And then a square is all of them because it meets the criteria of all of them. It has four sides. It's a quadrilateral. It has opposite sides that are congruent and parallel. It's a parallelogram. It has all the sides the same, so it's also a rhombus. And it has four angles that are right angles, so it's also a rectangle. So that's a good diagram to kind of see everything. The next page details just what I just said in more specific paragraph language. Turn two more pages and we get to this interesting picture that they made a rectangle in the middle of. You've got to find vertex A, and then immediately to the right vertex B, and then down to vertex C and vertex D. There's a rectangle in the middle of this photo. Not too sure why they chose to do that, but other than they wanted you to identify that that's a rectangle. And then if you move to the next page, page 328A, there's another figure that you need to identify. If you feel in the middle of the page, you'll feel this figure, and it has four sides and four congruent tick marks, and therefore they are, and then notice at the vertexes there's no right angle indicators. So you have a parallelogram here, but it's more specifically a rhombus. And then turn a few more pages over because the next few pages are just craziness to look at. Get yourself to a page break on page 329. It looks like 329F. There's a page break for 328F. There's a page break for 329, and it's going to detail the next very important three theorems about rectangles and rhombi. So we have these three theorems we're going to discuss about the diagonals of rectangles and rhombi. The first one is diagonals of a rectangle. So you have a model, you have a rectangle at the base of your page, and it's at the top of the print page. You have A, B, C, D. It's a rectangle. You recognize that you have four 90-degree angles, one at each vertex. There's diagonals going through from opposite vertex to opposite vertex, so from A to C and B to D. And the theorem is that the diagonals of a rectangle are congruent. So always, always, always in a rectangle, your diagonals will be the same measure. In a parallelogram, they won't. But in a rectangle, they will. And it can be proven by using a theorem, using our theorems and our congruency properties for our triangles. We could prove that, they bisect each other, and then we use the angles and our side angle side kind of stuff, and we could get to a space where we could prove that these two diagonals are congruent. But we don't have to. They give it to us in a theorem. We might have to later go backwards and prove why this is so, but just kind of put that in your brain to think about. But always remember that the diagonals of a rectangle are congruent. The next theorem on the next Braille page, 329A, shows a rhombus. A, B, C, D. A is in the top left, go counterclockwise, clockwise. B, C, D. Notice that there are tick marks on every side, so that means all four sides are the same, but it's skewed a little bit, so there's no 90-degree indicators at each vertex. However, there's a 90-degree indicator at the intersection of the diagonals. Notice they put diagonals in here, and they put a 90-degree indicator. And that's another theorem. The diagonals of a rhombus are perpendicular. That's what it says up above the drawing in print. And then down below it says AC is perpendicular. That's a good reminder of your perpendicular indicator. Shape indicator P, is perpendicular to BD. So all the interior angles where those two diagonals intersect are going to have 90, 90, 90, 90. Right? Not at the corners, but on the intersection in the interior of where the diagonals intersect will always be 90. And that's important to remember because maybe later we're going to use some of our right angle properties and theorems in order to solve for measurements of sides, because the side opposite those 90-degree angles, the side of the rhombus, would be the hypotenuse, wouldn't it, of those triangles. So we're going to end up needing that theorem potentially to use in order to use the Pythagorean theorem. Turn the page and you have the next theorem for rhombi, and that is that each diagonal of a rhombus bisects the pair of opposite angles. So they're perpendicular to each other. They bisect each other. They're not the same length because this is not a rectangle, but they do bisect the vertexes. Diagonals of a rectangle don't bisect the vertex. The diagonals of a parallelogram don't bisect the vertex. But the diagonals of a rhombus, because we have these four equal sides, they bisect the opposite angles. So it shows A, B, C, D, a rhombus, the equal sides with tick marks, the diagonals, and then at each vertex it labels the angles 1 and 2 at A. Those would be equal. 3 and 4 at B would be equal. 5 and 6 at C would be equal, and they would be equal to 1 and 2 because they're angles that are opposite, right? Opposite angles of a parallelogram are congruent. And then at D we have angles 7 and 8. The Braille's a little funky in that 8 was labeled up above it. Those would be equivalent, congruent, and they would be congruent to 3 and 4 because D is opposite B. Right? So it says that in the theorem, each diagonal of a rhombus bisects a pair of opposite angles, and then it says it in symbols about how the measurements of each angle are equal to each other. And then there's a paragraph of information on the next page to remind you about squares. It says a square is defined as a parallelogram with 4 congruent angles and 4 congruent sides. This means that a square is not only a parallelogram but also a rectangle and a rhombus. Therefore, all the properties of parallelograms, rectangles, and rhombi hold true for squares. So diagonals of a rectangle are congruent. Diagonals of a square are congruent. Diagonals of a rhombi are perpendicular to each other. Diagonals of a square are perpendicular to each other. Diagonals of a rhombi bisect their opposite angles. Diagonals of a square bisect opposite angles. So there's a drawing down below taking us through an example that where we need to find xz in square xyzw. And x is in the bottom left, and then they go clockwise, x, y, z, w. There's diagonals going through each vertex, and they intersect at point O in the middle. They're saying xz, so from left-hand bottom corner x to top right-hand corner z, that diagonal xz is 14. Or no, they're saying, I'm sorry, they want us to find xz, and they tell us that yw is 14. So I just gave it away, didn't I? You're all chuckling. Okay, so yw is 14. We know that a square is a rectangle, so therefore we get to use the rectangle theorem of diagonals of a rectangle are congruent. So if yw is 14, we know xz is 14. We could apply other principles here. We could say, what is xo? It's 7, because we know diagonals of a parallelogram bisect each other. All of those pieces would be 7, correct? And we know the angles in the middle, the YOZ and ZOW and WOZ and XOY, all those angles in the center, they're all 90 degrees because the diagonals are perpendicular to each other because a square is a rhombus, and diagonals of a rhombus are perpendicular. And then at each vertex at Y and Z and W and X, those diagonals are bisecting the vertex. So we know each set of angles is 45 and 45 because it's a square which has perpendicular or 90-degree vertexes, right angle vertexes, so it's all 90. And we know because it's also a rhombus, diagonals of a rhombus bisect a pair of opposite angles. So to bisect 90 means to split it in half and get 45. So we've got 45 at each corner. So we're creating a 45, 45, 90 triangle all the way around this. We're going to learn something about that later with special rules of triangles and right triangles in order to discover the measurements of the side. We could also use a Pythagorean theorem because we're going to have these legs being 7 each. We could go 7 squared plus 7 squared. That equals c squared, which is a side. 49 plus 49 is 98. The square root of 98 is 9.9-ish probably. So we know the side of this square is 9.9. So just keeping that all in your head for later to problem solve how to discover a measurement of a missing side if you're given that it's a square and you're given the measurements of the diagonal. All right, so it takes you through some exercises there that we just kind of talked through. And then we get to check your understanding for the rest of the section. So you can take a look at those, review those, practice those, maybe move on to more problems. Number 2 through 47 are excellent practice for this section. So I'd highly recommend you push yourself and practice some of those questions. At minimum, take a look at some of the tactiles and try to decipher them, figure out what kind of shape it is, what the diagonals are doing, remembering your theorems and rules around all of those diagonals. All right, that's it for 8-4, rectangles, rhombis, and squares. Do good thinking. See you in the next video.